Okay, binomial expansion. We're going to use Pascal's triangle. This should be a review. Just a quick reminder. I want to highlight something real quick. This is row 0, and these are all entry 0. So we start counting with 0 here. So there are some other patterns I just wanted to pull your attention to. One of the more obvious ones, we see 1, 2, 3, 4, 5, the counting numbers, but then we get these triangular numbers too. You get different patterns if you color in different types of numbers. This one's called Pascal's flower. The product of the yellow petals should equal the product of the orange petals. And then you can also see Fibonacci's sequence. If instead of going directly up, if you go up 1 over 1, you should get an entry in the Fibonacci sequence. But the pattern that we're going to look at today is the fact that each one of those entries in Pascal's triangle, it can also be found using the combination, where the combination describes the entry. So, for example, this entry here says we're in row 0, entry 0. This one here would be row 1, entry 0. And this one is row 1, entry 1. And so let's go down here to the 4th row. This could be, I could figure out what number this is going to be by taking 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, and 4, choose 4. So the whole point of looking at this is because you already knew that if you knew Pascal's triangle, you could expand a binomial. Maybe you didn't know, maybe this is review, but if you know combinations, you can find the appropriate row of Pascal's triangle so you can expand a binomial. We'll take a look at an example after I just show you what this formula looks like a little bit more formally. What this is saying here is that for each term, we have a different coefficient, which is going to be different entries in the Pascal triangle. And for each term, the first number in the binomial starts off with the highest exponent and works its way down. And the second term from the original binomial starts off at the 0th power and works its way up. Well, not 3 there, but we're going up until it gets to the highest one, and then there's no A here. And just to clarify, R is the entry. All right, so if we're doing an expansion to the 5th power, we need to know. We need to know 5 choose 0, 5 choose 1, 5 choose 2, and I can actually stop there. We can cheat and look at the 5th row. The Pascal's triangle is symmetrical. So once you know half, or in the cases where there are odd entries, you have to know up to that middle term, the other side's going to repeat. So 5 choose 0 is 1, 5 choose 1 is 5, 5 choose 2 is 10, and then the other side's going to go 10, 5, 1. So we start off with a coefficient of 1, take the first term, raise it to the highest power, and the second term is to the 0th. Take the next coefficient, lower this exponent, raise this one, next one, lower that one, raise the 2 to the 2nd power. Now work our coefficients back down. Drop this to 2, raise this to 3. Raise this to 4. And Oop, that one's to the 0th. Raise it to the 5th. So all together we get x to the 5th plus 10x to the 4th plus 40x to the 3rd plus 80x squared plus 80x plus 32. Alright, so let's try expanding this binomial. I should actually have labeled this one a little bit harder. We're only raising to the 4th power this time, but we have a little bit more going on because we have two variables and this variable has an exponent. So let's go ahead and figure out the coefficients. We want 4 choose 0, 4 choose 1, and 4 choose 2. Then they repeat. So we go 1, 4, 6. So altogether that's 1, 4, 6, 4, 1. So let's take this slowly. Coefficient of 1, 2x to the 4th, start at the highest, and then the negative y squared is to the 0th. I'm going to keep writing plus despite this negative here. Plus 4 times 2x to the 3rd times negative y squared to the 1st plus 6 2x squared negative y squared to the 2nd plus, back down to 4, 2x to the 1st, negative y squared to the 3rd, plus 1 times negative y squared to the 4th. You might want to pause it and work out what these are on your own. I'm going to write out the finished expansion. We have 16 x to the 4th minus 32 x cubed y squared plus 24 x squared y to the 4th minus 8x y to the 6th plus y to the 8th. A lot better than trying to distribute, but still not great. Just a little bit of insight here. Not a whole bunch of applications that the typical person is interested in, but probability and economics both use binomials and their formulas. Physics, you might have to expand a binomial within a formula, and in calculus as well. And we might get to de Moivre's theory when we get to trig, and we use binomial expansion there. So I want you to try these on your own. We'll go over the answers in class. You'll get an assignment tomorrow that's based on this topic.